effect of pressure and temperature on the Rankine cycle. Let us first consider the effect of exhaust pressure and temperature on the Rankine cycle. Exhaust pressure and temperature. Effect of pressure and temperature on Rankine cycle. On the Rankine cycle. Let us first consider the effect of exhaust pressure and temperature on the Rankine cycle. Exhaust pressure, for example, P4. This point, drop it to P4 prime. With the corresponding decrease in temperature at which heat is rejected on Rankine cycle. This line. The network is increased by the this effect shown on the TS diagram in this picture. 1, 4, 4 prime. Exhaust pressure, for example, P4. This point, drop it to 1 prime, 2 prime, P4 prime. With the corresponding decrease in temperature at which heat is rejected, shaded in blue, and now yellow. The heat transfer network to the steam increased by shaded area 1 prime transfer 1, 4, 4 prime. One prime, 2 prime, 2, 1. This increases the area of shaded in blue and now yellow. The heat transfer to the steam is increased by 2 prime. Heat transfer and A prime. 2 A prime. Increases by area of this area. Since these two areas are approximately equal, so A prime, 2 prime. These two areas approximately equal. And A prime. 2. The net result is an increase in cycle efficiency. This area. Since these two areas are approximately equal, so heat rejected. These two areas approximately equal. This is is also evident that the net result is an increase in average temperature at which heat rejected is decreased. Note that, however, that lowering the back pressure causes the moisture content of the steam leaving the turbine to increase. This is a significant factor because if the moisture in the low pressure stage of the turbine exceeds about 10%, not only is there a decrease in turbine efficiency, but erosion of the turbine blade may also be a very serious problem. This is also evident that from the fact that the average temperature at which heat rejected is decreased. Note that, however, that lowering the back pressure causes the moisture content of the steam leaving the turbine to increase. This is a significant factor because if the moisture in the low pressure stage of the turbine exceeds about 10%, not only is there a decrease in turbine efficiency, but erosion of the turbine blade may also be a very serious problem. So it's another increase. And the average. Note, however, that lowering the back pressure causes the moisture content of the steam leaving the turbine to increase, and it causes to increase moisture. The average temperature steam T average in point Q out decreases out. So eta thermal increase turbine and note, however, that lowering the back pressure causes the moisture content of the steam leaving the turbine to increase, and 10% cause to increase some serious moisture in the steam, such as erosion point out. Next, consider the effect of superheating the steam in the boiler turbine. So, effect of increasing temperature. It exceeds about 10%. It causes some serious. Consider the effect of superheating the steam in the boiler, such as erosion. Next, consider the effect of superheating the steam in the boiler. So, effect of increasing in the picture temperature. Superheating means that the saturated liquid PART 3 converts to superheated. Consider the effect of superheating the steam in the boiler. 3 from this point at this point, we see that the work increases the area as shown in the picture here. 3 prime. Superheating means that the or 3 saturated liquid 3 prime 4 prime 4 at 3 converts and to the heat transferred in the boiler is increased by at 3 prime this point and this point. We see that the work increases the area 4 3 3 prime 4 3 3 prime or 3 prime 4 prime 4 B, and the heat transferred in the boiler is increased by, since the ratio of these two areas is greater than the ratio of net work to heat supplied for the rest of the cycle, it's evident that the given pressure superheated the steam increases the Rankine cycle efficiency. By the area of 3 prime B prime B, this area. Since the ratio of these two areas is greater than the ratio of net work to heat supplied for the rest of the cycle, it's evident that the given pressure superheated the steam increases the Rankine cycle efficiency. 3 prime 4 prime 4 on the 3 prime B greater than the rest of the cycle. So we have 1 2 3 4 1, the area of the ratio of these two areas. 1, consider this picture E A 1 3, we have increase in 3 prime 4 prime 4 on the 3 prime B prime. This increasing efficiency would also follow from the fact that the average temperature at which heat is transferred to the steam is increasing. 2 3 4, this 1 increase on the 1 is due to 3 B A 1, we have increase in efficiency. Increasing T average. This increase in efficiency would also follow from the fact that the average temperature at which heat not also that when the steam is superheated, the quality of the steam leaving the turbine increases, and also this increased quality of the steam increases due to finally the influence of the maximum pressure of the steam must be considered. Increasing T average at Q Note also that when the steam is superheated, the quantity of steam leaving the turbine increases, and also the quality of the steam increases, and it's shown in the picture here. Finally, the influence of the maximum pressure of the steam analyzes the maximum temperature of the steam as well as the exhaust pressure. T max, the effect of steam, and P max, influence of the maximum pressure constant. The heat rejected decreases by the area of the picture B prime 4 prime 4 B prime. This area in this analyzes the maximum temperature of the steam as well as the exhaust pressure. T max heat rejected, Q out, steam, and P max decreases exhaust pressure constant, G prime 4 prime. The heat rejected decreases by the area of B prime 4 prime 4 B prime, this area, Q up. The network increases by the amount of single cross hatching increases this area, G prime 4 prime, then we go from the G to 4 B at temperature constant. We should reach a point B prime as isotropic to a G prime, so the work increases by the hatch. The network increases by the amount of single cross hatching, single hatch, this area, and decreases by the amount of double cross hatching. Then we go from the other G to, and we have also a temperature constant, and the decreasing in reach a point B prime, so which means as isotropic to we can run G prime, so the work increases Q out by the hatch, decrease W single hatch, increase as the single hatch, and decreases by the amount of double cross hatching, and decrease. And the other hand we have also double and a decreasing in work hatch, so it means so we can decreasing Q out, decrease W net. Therefore the network tend to remain the same, but the heat rejected increase. Single hatch, and decrease a double hatch, the work tends to be same, and the heat rejected. Therefore the network tend to remain the same, but the heat rejected decrease. The work tends to be, and hence the RANKINE efficiency increase, and the heat rejected decrease. With an increase in maximum pressure. And hence the RANKINE efficiency increase. Note that this instance to average temperature at which heat is supplied increase With an increase in pressure, the quality of the steam leaving the turbine decreases as the maximum pressure increases. To summarize this section, we can say that network and efficiency of the Rankine cycle by with an increase in maximum network pressure and efficiency Note that this instance to average temperature at which heat is supplied Rankine cycle. With an increase in pressure, the quality of the steam leaving the turbine decreases as the maximum pressure increases. To summarize this section, we can say that network and efficiency of the Rankine cycle by lowering the condenser pressure, network and efficiency of the Rankine cycle by increasing the pressure during heat addition. Can be increased by lowering the condenser pressure, and by increasing the pressure during heat addition. Superheating this. Increasing pressure during heat addition, lowering the condenser pressure by superheating the steam, and by the quality of the steam leaving the turbine is increased by superheating the steam and decreased by lowering the exhaust pressure and by the increasing pressure during heat addition. These effects are shown in various pictures. Superheating the steam. Here, the quality of steam, increasing pressure during heat addition, lowering the condenser pressure by superheating the steam. Leaving the turbine, the quality of the steam leaving the turbine is increased by superheating the steam and decreased by lowering the exhaust pressure and by the increasing pressure during heat addition. These effects are shown in various pictures. Here, the quality of steam decreased by lowering exhaust pressure leaving the turbine is increased by superheating and also decreased by the steam and increasing pressure, decreased by lowering exhaust pressure during heat addition. Quality and also decreases. These effects are shown in the figure 11.7 and 11.8. Decreases by in connection with this consideration, we note that the cycle is modeled with 4 known processes between the 4 states with a total of 8 increasing pressure. Assume state 1 is saturated liquid. We have 3 parameters to determine during heat addition. The operating conditions are physically controlled by the high pressure generated by the pump. Quality. Operating. These effects are shown in the figure 11.7 and 11.8. In connection with this consideration, we note that the cycle is modeled with 4 known processes between the 4 states with a total of 8 physically controlled by the high pressure saturated liquid. We have 3 parameters to determine. The operating conditions are physically controlled by the high pressure generated by the pump. The operating conditions are generated by the pump. Physically controlled by the high pressure, superheated to T3 and the condensate temperature T1. Generated by the pump. P3. The superheated to T3 the result of amount of heat transfer to the that takes place. The next section is another cycle, the reheat the condensate temperature T1. Which is the result of amount of heat transfer to the that takes place. The next section is another cycle, the reheat cycle.